All right, welcome back to another video. Today, what we're going to talk about is turbo machines. In particular, we're going to really focus on pumps and provide an equation for your shaft power going into the pump. Okay, so if we look over here, there is a lot of companies that need pumps, small pumps, big pumps, and they move liquids. Okay. Your heart is also a pump. Okay. It's providing a liquid. Before I show you some other things, uh, again, pumps move liquids. Fans are gas pump with low pressure rise and a high flow rate. Blowers are a gas pump with high pressure rise and high flow rate. And then compressors are a gas pump with high pressure rise and low flow rates. Okay. So you want to know, in particular, like what you're talking about. What we're going to focus on today is looking at pumps. Okay. I'm going to show you an equation, and then we'll get into like this particular graph here, where you can actually find the operating point that you need. Okay. So let's go ahead and write some stuff down. So let's look at pumps. Pumps. Okay. Now I'm going to write the first law of thermo. Okay. And then we're going to use this and draw a sketch of a pump and go through this. Okay. Now, this is actually a good intro to what you're going to be doing in thermodynamics. Okay. So let's go ahead and write what I like to call like the big energy balance equation. Whoops. So we got delta KE plus delta PE plus delta U equals, we're going to do it per time. So we're going to write everything per time. Okay. This would be the work out minus the work in plus Q dot out minus Q dot in plus the energy of the, energy of the fluid out minus energy of the fluid in. Okay. Now, just to give you an idea, we're not going to get into too much detail, and I'm going to probably erase what I'm going to do here. But on the left, delta KE, delta PE, that's kinetic energy, potential energy, and delta U is your internal energy. Okay. Usually, what you do in physics, where you have potential energy, conservation of energy of a ball falling, that's this left side of the equation. Okay. And delta U is your internal energy, and it depends on temperature. So if your temperature of the ball changes, you would incorporate it. But a lot of the times we neglect that. So we don't have the delta U term in physics. Now on the right-hand side, this is stuff that's going through a boundary. Okay, so say you had a pump here, which I'll show you. You have shaft going in and you have fluid energy coming in and out. Okay, so this is what we call work. This is your heat transfer. And this is your fluid energy. And inside this fluid energy is where we have the Bernoulli's equation. Okay. Now, I'm going to draw a pump right here. Very simple pump. And let's do this and let's do that. Let's have, we have shaft, and then we have fluid coming in, and we have fluid going out. Okay. So a pump, we have a shaft that's attached to a motor. I'm not going to draw the motor, okay? But that motor you have electric power in, converts the shaft. So this shaft is spinning. You have shaft power. And basically it's sucking energy in from from here, okay? And then it spits it out up there, okay? All right, so these energies that I've driven are basically are on this side of the equation, okay? Now, if this pump was moving in space and completely changing temperature, then you would have stuff over here on the left, okay? But we're assuming it's steady state and not moving, okay? So what we can do is we can cancel some stuff. And not moving in space, there's no temperature change. There is only mechanical shaft, okay? Which you would have basically coming in, okay? There's no heat transfer, and you have energy fluid in and out, okay? All right, so what we have now is I'm going to move this over. We have the shaft, which is coming in, okay? The energy of the fluid out minus the energy of the fluid in, okay? So this I just defined as W shaft and brought it to the left of the equal sign. Okay, now I'm going to write this W shaft equals M dot, and this is where you have your Bernoulli's equation, okay? Minus M dot 2, oh, we'll call this M dot 1, M dot 2, P2 over rho plus V2 squared over 2 plus GZ2. Now I am, there is a few things I'm missing, but for what we're trying to accomplish in this video, this is good, okay? So fluid energy, you have to multiply by mass flow rate times basically the Bernoulli's. And that becomes now basically a watt or energy per unit time, okay? But we also know that steady state conservation of mass states that whatever comes in must equal what goes out, flow rate. So M dot 1 will equal M dot 2, and we'll end up, I believe, calling that M dot, okay? Now, we can cancel some things in this particular Bernoulli's equation, okay? We're going to assume that the velocity and there's no elevation change, or the elevation change from here to here, we're going to neglect. So we can take those two, and we're going to call M dot 1 and M dot 2. So what we end up having now is M dot over rho P1 minus P2. Okay. We can write this again as rho AV as for mass flow rate, okay? And those cancel, and we end up with volumetric flow rate times delta P, okay? So if we want to know the shaft power going in to this pump, okay, we as long as we know the flow rate and we know delta P, okay, that's the reason I kind of did this. And it's a good start and to understand a little bit of thermodynamics when you get to it. Okay. Now, you might not see this in fluids, particular. You can actually see this. There's another way to write fluid energy. Okay. Watch. I'm going to do this and show you what we can do. HP is P1 over rho G plus V1 squared over 2G plus Z1 minus P2 over rho G plus V2 squared over 2G plus Z2. All right. Now, if you remember, this is like fluid energy in and out, okay? All these units now have a unit of like head or meters or feet, okay? So I just kind of changed it that way. And I define this as now HP. And what we're going to do is, again, we can take out these values here. And so HP becomes delta P over rho G, or delta P now becomes rho G HP. Okay, so what we can do is we can now plug that into here. So the shaft becomes V dot rho G times HP. Okay, so I just kind of wrote the fluid energy in and out differently. I defined it differently, which you can, just to kind of make it so now we can have a shaft power equation that's related to the pump HP value. Because where do we see this? We have that in our modified Bernoulli's equation, remember? So I just kind of wanted to show you where this equation kind of comes from. So as long as you understand kind of the basics, you're fine. Okay. So we're going to use this equation in one of your in your homework and the final exam. Okay. Now we know that the shaft power has to be greater than this rho GHP. Okay. Basically, it's the energy in and out. Okay. That total energy has to be greater. Okay. And we're going to call this WP. Okay. Of the propeller, because there's a propeller in the pump. So we can define an efficiency that's the output power over the input power, which is V dot rho G HP. And you will see sometimes this called BHP, or lowercase, which is brake horsepower. That's just your shaft power. Okay. So I'm pretty sure one of the homework questions goes through, okay, if the efficiency is say 80%, what is your actual shaft power? So what you would have to do is you take your V dot rho G HP and you divide by the efficiency. Okay, because this is always going to be greater because you lose energy. Okay, from heat, from vibration, from sound, whatnot. Just the expansions, right, of the water, or the propellers aren't very efficient. So this is technically the overall equation you would use to find that shaft power. Cool. All right. I kind of hope that makes sense. Next thing I just want to show you is there is a particular, and I'm going to go through this, so there's going to be a video to help you. But you can find basically your operating point of a pump, and that would be your maximum or best case. And anything to the left you can use, because anything to the right of this line you can't. So let me explain. Okay. Let me take, let's do green. So let's look at this blue solid line that I'm tracing right now. Okay. This is, on the y-axis is H, your total head. So meters, feet. Bottom, volumetric flow rate. This line I just drew, that is your available amount that you can get from the pump. This is from the manufacturer, okay? So the manufacturer gives you a spec. It says, based on your flow rate, this is how much H value you're going to get, the available value, okay? Okay, so that's from the data sheet. That's what you're going to get, okay? It's like saying, here's a temperature sensor. This is the temperatures you're going to get, okay? The bottom, this red, and I'm drawing it and now in black, this is your system curve, or what's required based on your pump. Well, based on the pump value you need, but it's based on the length of the pipe, the elbows, the losses, the velocities, and all of that. Okay, so it's your system. So you have a system that has 20 feet of pipe, and it has 5 elbows, it has a valve, and you can calculate this. We've been doing this with the modified Bernoullis. So you plot this based on volumetric flow rate. Okay. And when these points cross, that is your operating point. You can use this value. Typically, you should use this value, but you can use all the values to the left as well. You just can't use anything to the right because why? Because you need here, if you pick this point right here, that is higher than this point. Your pump cannot provide anything in this region here. You can't get, the pump cannot do that. It's not designed to do that. Okay. So you can't run this. You will never, if you have a system, your pump will never be able to get to that flow rate, and never, you might not even see flow in that system because your pump cannot provide that much H or head into the system. Okay. So this is basically your performance curve, finding your optimal operating point based on the manufacturer specs and your system. And I'm going to go through an example on this, which is your final project. So stay tuned. Okay. So I hope this is a good understanding of like pumps and fan. Like you can analyze all these with fans and blowers and compressors too because they're gas. But I like using liquids because a lot of the companies use pumps. Okay. And as long as you understand, we're going to use this as your equation and understand that we have an operating point based on your pump, and you can find that. Then you should be pretty good. All right, thank you. And if you have questions, let me know. Bye now.